Welcome back. In a previous lecture, we talked about sampling methods and various types of sample. In this presentation, we will discuss power analysis. It is basically how to calculate power and sample size for your study. In your grant proposals, you will most likely need to put in a justification for resource allocation. This comes from your sample size calculation. So I want you to understand by the end of this lecture what sample size you will need to detect a specified difference between two groups you are studying. Or, given a sample size, you may want to know if you have adequate power to discriminate between effects. Okay, first let us understand what is the motivation and background behind power analysis. Power and sample size calculation is an important part of a survey research. Power of a study is basically our ability to detect a true association or effect in a study sample when our exposure of interest is indeed associated with the outcome in the target population. Remember, we do not get to observe or study the target population. We simply get to observe the sample and then we generalize the sample results back to the population. However, remember the effect we see could be a result of random chance as well. Therefore, we need a sample size large enough to be able to distinguish a true effect from a random variation. Power analysis enables us to justify the resources we need to utilize in a study when we submit grants for IRB approval. So this is important. This is really a revision for you. We usually talk about power in the context of a hypothesis testing. Power is the probability of rejecting the null hypothesis when null is false. It is the probability of detecting a true association when it exists. Null hypothesis states that there is no difference between the two groups. And when you reject the null when it is true, you commit type 1 error or alpha. We usually set alpha to 0.05 or 5%. The graphs make it easier to understand power. The distribution on the left shows the scenario under null hypothesis. We usually set the type 1 error or alpha, as I said, to 0.05 or 5%. And the probability of type 1 error is basically the p-value. P-value of 0.05 means that the probability of seeing the effect estimate due to chance is 5%. The graph on the right shows the scenario under alternative distribution. Power is the area under the curve to the right of the critical value. It is 1 minus beta. And beta is your type 2 error. That is, basically you fail to reject the null hypothesis when it is false. Remember that either the null is true or alternative hypothesis is true. They both cannot be true at the same time. Okay, here are some FAQs for power analysis. We already talked about why we do power analysis when we discussed the motivation. So in the coming slides, we will learn what is a power analysis, how to do a power analysis, and what happens after a power analysis. What are the determinants of power calculation? In other words, what do we need so that we are able to calculate power for a study? Several factors influence power. Power and sample size are interdependent. You calculate power given sample size, or you calculate sample size given a power. We can increase power by increasing sample size. This is really the best way to increase your power. It is under our control, and larger the sample size means greater power. This is because as your sample size increases, the variance decreases. Okay, let us discuss more the effect of sample size on power. Take a look at these two distributions under null and alternative hypotheses. Say we have a relative risk estimate of 2 under alternative hypotheses, and say we have a type 1 error of 5%. Now what happens if we decrease the sample size? Alright, as we decrease the sample size, the type 2 error increases and the power decreases. You can see that the shaded area under the alternative distribution, that has expanded. the relative risk decreased from 2 to 1.5. Notice that the means under null and alternative hypotheses get closer to each other. The entire distribution under alternative hypothesis actually moved closer to the null distribution. So with a decrease in power, our ability to distinguish a true effect from that due to random chance got less. On the other hand, as we increase the sample size, the type 2 error decreases and the power increases. The relative risk estimate increased from 1.5 to 3. Notice that the means under null and alternative hypotheses get further apart. The entire distribution under alternative hypotheses moved further away from that of null distribution. Okay, we just talked about the influence of sample size on power. There are other factors that influence power. The second way to increase or decrease our power is to increase or decrease your effect size. Here, the relative risk or the effect size under alternative distribution is 3. Now, if we increase the effect size to 4, then the entire curve under alternative distribution will shift to the right. And you can see that the power will increase. The overlap between the two distributions become less. Alternatively, if we decrease the relative risk to 2, then the whole curve will move to the left and hence the power decreases. So this is another way. However, this is rarely done. Investigators may do this when you exhaust all means of increasing the sample size. Third, as you decrease the critical p-value or the type 1 error, the type 2 error increases and the power decreases. If you increase the critical p-value or type 1 error, power increases. There is a trade-off here. You get more power at the rate of higher false positives. Usually for interventions that have minimal side effects but have beneficial effects, you may want to have a higher power of detecting that effect. For example, if a vitamin is thought to have protective effects for heart attack, then we really do want to detect whatever level of protective effect it has on preventing heart attack. And we are not too worried about a false positive result since the vitamin is quite harmless. Therefore, we may be able to accept a higher level of type 1 error, say 10%. This will increase our power. Mostly, we don't want to have more than 5% type 1 error rate, and power is typically lower in a two-sided test. And when you move from one-sided to two-sided, basically you are decreasing the critical p-value. So you could see all these from those two distributions that I showed under null and alternative, and as you move critical value here to there, then you will see how the power increases or decreases and how type 1 error rate or type 2 error rate increases and decreases. Fourth, your standard error may be big if the sample size is small or there is a lot of variability in the population. This could happen if you have subgroups in the population that are quite different. In such cases, you can use cluster sampling and then adjust for design effects. Remember, design effects is a ratio of sampling variance under cluster sampling to that under simple random sampling. Higher design effect means higher sampling variance in cluster sampling, while which really in turn means that the sample size is less because the sampling variance is inversely related to the sample size. So in a nutshell, the best way to increase your power is to increase your sample size. That's really what I wanted to tell you. Okay, we just looked at the ingredients for power analysis. In a power analysis, we either calculate power based on a given sample size or calculate sample size based on a given power. In many of the grant applications that we submit, we calculate the sample size based on a given power to distinguish a true difference between two groups. We then decide on a test statistic, which could be mean, proportion, relative risk, odds ratio, etc. Usually we set type 1 error rate to 5%. Effect size is basically the difference in the measure of the outcome between the two groups. So with all this info, now we are all set to calculate power. Okay, let us first see how to calculate power based on a given sample size. After that, we will calculate sample size based on a given power. So this is the formula for power calculation. It looks a little scary, but if you really follow closely, it is not that bad. As you can see, we need some values to calculate the power. First, we need the z-value. z1 minus alpha is the z-score at which we reject the null hypotheses. For 95% confidence interval, z-value is 1.96. Then we need the values of standard error under null hypotheses and under alternative hypotheses, and then the mean differences under null and alternative hypotheses. So mu naught is the mean difference between intervention and control group under null hypotheses, and mu is the mean difference between intervention and control group under alternative hypotheses. And remember that under null hypotheses or under the null distribution, there is no difference between the two groups, so the mu naught should be 0. And you have here the formulas for calculating standard error under null and alternative distribution. And I've given you here the formulas for calculating standard error under null and alternative distribution for the proportions. I said proportion because we are going to use proportions for one of the examples that we are going to discuss to calculate power. Okay, this is the formula for calculating power for proportions. So you can see again that here the P naught is the difference in proportions under null hypotheses. That is, it'll be 0 because under null there will be no difference. And then P would be the difference in proportions under alternative hypotheses, basically the difference between the two groups, the intervention and the control group. And P1 is basically the proportion in the exposed, and P2 the proportion in the unexposed group. And Z1 minus alpha is basically the Z score at which we reject the null hypotheses. And for 95% confidence interval, we have usually Z value of 1.96. For standard error, I gave you the formula for calculating it in the previous slide. Okay, let us calculate standard errors first. And we'll do this with an example. Let's assume a hypothetical situation in which the cure rate of tuberculosis patients who are given vitamin D is 80% and cure rate for those not getting vitamin D is 70%. And you are given a sample size of intervention and control groups, and that is 200 in each group, so 400 in total, and you are testing the hypothesis at a significance level alpha of 5%. And note that the P bar is the mean of two proportions, basically 0.75. The mean of 0.8 and 0.7 is 0.75. And you just need to plug in the numbers and you get your standard errors. Okay, now we have our standard errors, and then we are all set to calculate power. We have two-sided test and a z-score of 1.96, and you just need to plug in the rest from the previous slides, and you get a power of 63.7% to detect a 10% difference in cure rates based on receipt of vitamin D, right? It's 10% because 80% minus 70% is 10%. So this doesn't look like sufficient power. I mean, 63.7%. I would try to get more than that. So we may have to think about increasing the sample size or relaxing the type 1 error. Well, here is the easy way to calculate power using software. This output is from Stata. The code you type is in red, and all you need to specify are the proportions and your sample size. And if you do not specify, it assumes a type 1 error rate of 5%. And we obtain exactly the same power as our hand calculation, 63.75, which is really reassuring. Though you will not do these calculations by hand in practice, it is really good to understand the mechanics behind power calculation. What is happening when you are typing in the commands in the software program and hitting the enter key. Okay, so we just calculated our power, and now let us look at sample size calculation. So this is what you may be mostly doing, especially when you are submitting grant proposals for a study. You almost cannot escape calculating sample size. So to calculate sample size, you need type 1 error, power, effect size in the exposed and unexposed group, and this usually comes from a reference study conducted in the past. This is the formula for calculating sample size for relative risk. Relative risk is the risk in the exposed group divided by risk in the unexposed group. And again, P1 is proportion in the exposed group and P2 is the proportion in the control group. So basically, exposed group is the intervention group and the unexposed group is the control group. So don't get confused over the terms. Beta is type 2 error and 1 minus beta is your power. And then the proportions P1 and P2 here of 0.8 and 0.7, they are from the vitamin D and tuberculosis example. So we are going to use the same example to calculate our sample size. Now you can plug in values from the previous slides and you will see that we will need a sample size of 303 in each group and 606 in total to detect a 14% increase in risk with a power of 80%. I really don't feel comfortable saying increase in risk because we are talking about cure rate here from use of vitamin D in TB patients versus not using it. And we have a relative risk estimate of 1.14, so that makes it 14% because 1.14 means there is 14% increase in risk. Alright, so looking at the other way around, we saw in a power calculation that at a sample size of 200 per group, we are able to get a power of only around 63%. Now from this exercise, we see that if we increase the sample size to around 300 per group, we can get a power or a discriminating power of around 80%. So again, this is the easy way from Stata, and we obtain almost exactly the same sample size. So we have a sample size of 307 in each group and 614 in total. So the command line that you type in is power to proportions, and then you specify the baseline risk, which is 70% or 0.7, and then you specify the relative risk you are interested in, which is 1.14. And if you do not specify specifically, then it assumes a power of 80% and a type 1 error of 5%, and Stata would do it for you. Okay, that was the power analysis using the formulas and hand calculation. You can also calculate sample size using the power chart. However, you need to have effect size for that, and effect size is the difference in the means or proportions between the two groups. Note that you have to convert the proportion to arcsine value for calculating the effect size. We do the arcsine transformation because the absolute difference in proportion is not an appropriate representation of effect size. It depends upon the actual values that go into generation of the mean or the proportion. Say the power to detect a 20% difference between proportions, say P1 of 0.8 and P2 of 0.6 may be different from the power to detect a difference of 20% between 0.4 and 0.2. Usually the power is less for rare outcomes. Therefore, we do arcsine transformation. So the figure 7.2 on page 171 of your textbook has that arcsine transformations that you can directly use and then plug in. So again, for our TB and vitamin D example, let us try to calculate the sample size using the power chart. You obtain your values for arcsine transformation from the table in your textbook and then calculate the effect size for proportions, which came out to be 0.232. So using your power chart against this effect size value of 0.232 and 80% power, you will get a sample size of around 630 or 315 per group, which is really close to what we just calculated from our formula and with Stata. And this is how you calculate your effect size for difference in mean, where mu is your mean and standard deviation is sigma. So here are some rules of thumb regarding deciding how big is your effect size. Your Ade and Cornelius textbook has small effect size as less than 0.5 and large effect size as greater than 0.8. And then the effect size for means or proportions from Cohen is also quite similar. For correlations, the actual correlation coefficient between two variables is the effect size. And the correlation of 0.1 is considered small and 0.5 is considered large. And 1 means, as you know, perfect correlation. This table is from your Ade and Cornelius textbook on page 178. There are adjustments that you need to make to the sample size after your power analyses based on a number of factors. And these adjustments are all really given in your textbook, and I recommend you go over them if it doesn't become clear to you here. And the first adjustment is for your population, for the size of your population. Basically, you adjust your sample for finite population correction. You may need to adjust for it because your sample is usually small and population is large. And as your sample size increases and approximates the size of the target population, then there is less sampling error and you don't have to adjust for finite population correction. So basically, finite population correction, or FPC, is simply the proportion of the sampling frame that is not sampled. Because, out of the entire frame, you're sampling just your sample and there is this huge chunk that you are not sampling. So it is 1 minus sampling fraction, which is your finite population correction. So for large sample size, then your sampling fraction is usually small, and hence 1 minus f is almost equal to 1. And we can ignore the finite population correction. So in this example, we have a really large population size of 250,000, and we have a small sample size of 384. Therefore, that finite population correction does not really come into play, and you can see that even after adjustment for finite population correction, you get the same sample size, but it may not be the case if your population size is small. Second, if we are using a cluster sample or a complex sampling method, we may have to adjust for design effect resulting from such sampling. We saw that design effect arises from cluster sampling. for example, say the design effect is 1.3, then we multiply our estimated sample size by the design effect to obtain our new sample size. So in this example, we multiply our estimated sample size of 384 by 1.3 and we get 499. So that is your new sample. So based on that new sample, you'll look at conducting your study and allocating your resources, etc. So third, you need to adjust for response rate. So this is really more intuitive and straightforward. If the response rate is expected to be poor in your survey, then we will need to adjust for it by increasing our sample. And we do that by dividing the sample size by the response rate, as you can see here. So in this example, after adjusting for design effect and response rate, your new sample is now 624. And then the fourth adjustment is for ineligible units. The concept is really similar to adjustment for non-response. You will come across ineligible elements in your sample, definitely, and you need to adjust for that. Remember, in that telephone survey example, households belonging to commercial units are ineligible, so you may need to adjust for those things. Here it is estimated that 10% are ineligible. So accordingly, you adjust your sample for that, and our final sample size now becomes 693. And all along, you really need to keep an eye on the cost. How much resources are available and whether that is sufficient for the sample that you have. Often you will need to make adjustments. For example, you may need to move from simple random sample to a cluster sampling based on the funding limits. Okay, with this we have come to the end of our lecture on power analysis, and we have some exercises for you on power analysis in the interactive lecture that will make you feel more comfortable about it.